Yeah, sorry. Sorry, Austin, my bad. Um, can everyone hear me?
Yeah, everything's fine.
Oh, great. Okay. Cool. Right, Austin, whenever you're ready.
All right. Um, um, so good morning. Uh, we are going to present to you the original method of the Gaussian integral. So the most common proof for the Gaussian integral is the polar coordinates method, as it is the fastest and easiest to follow. You first square root the whole integration, and you plot out the graph of e to the power of negative x squared plus y squared, which will be 3D. Your goal is to find the volume under the graph. So you first divide the volume under the graph into many tubes. If you take one tube out and cut it open, you get this rectangular shape with the height of e to the power negative r squared, and length would be the circumference of the tube, which is 2 pi r, and the thickness will be dr. You get the volume of one tube by multiplying them together, and the volume of the entire graph by integrating it from 0 to infinity. And with that, we will get pi. And we know that the solution of the squared integral is pi, and hence the original Gaussian integral solution is square root of pi. But that is not what we are going to talk about today. The method we are going to use is the original method by Laplace,
Laplace,
which
yeah.
uses a hidden Gaussian integral and the formula for Euler to prove. The formula of Euler is introduced without any explanation at all. So we decided to use Wallis' method to give a better explanation of the solution and especially to understand Euler's method. We choose this method because it uses a range of techniques we learn in class, and we have to derive more working in some sections for ourselves, as this is pretty hard and we have to skip over some of the more elementary steps.
So in terms of structure, we're going to start with the original method and show that that was Laplace's starting point, and it's actually just a hidden Gaussian integral. And then we're going to move to the method of asymptotic estimates, which Austin just mentioned. We're just going to do a brief overview, prove the relevant inequality, and then transform that inequality to resemble Euler's formula. And then we're going to come from the side of Euler's formula and transform that side so that it resembles the inequality. So they're sort of going to meet in the middle a little bit. And then we're just going to return to, once we've sort of showed the relevance of where Euler's comes from, then we're going to return to the original method and prove a relevant claim, and then substitute the formula back into our starting point from Laplace, and then just solve. Okay, so just in the interest of time, we're going to have to I'm going to skate over some of the working, but we've been pretty careful with deciding what to omit for this presentation so that you can still get a good theoretical understanding of this method. And this is a graph of the Gaussian integral that we just did in Python. Okay, so for the original method, this is where Laplace started from. And he used that as a preliminary to get to the Gaussian integral, which we have here. And to do that, it's a u substitution. It's not too difficult. Just let u equal root negative ln x. And so this is the working for that. And then as you can see, we end up with the Gaussian integral. But it's not a trivial starting point. It is relevant for the method, and we'll see why a little bit later on. So now for the method of asymptotic estimates. So you start with this inequality here. And the general concept of this method is to squeeze or to pin down the Gaussian integral to a value of root pi over 2 by proving that it can't be greater or smaller than our upper and lower bounds. And so we made a graph on the Cartesian plane in Python to illustrate this concept. So here the Gaussian integral is the green line, and then the lower and upper limits are the red and purple lines. That's just the code. Okay, so now we're going to prove this statement because it's relevant for Euler's, for how we get to Euler's formula. So for the lower bound, we rearrange, and then so we have 0 on this side. And then notice that this bound holds if and only if the function's non-negative. So typical proofs, sorry, I've jumped to the wrong place. Yeah, so because this is an even function, we only need to show that the function is greater than 0. And if we derive and then set to 0, we find a critical point at x equals 0. And then if we just use a test point, we know that the function is increasing on the interval from 0 to infinity. So the function has to be positive. So we've established this side of the inequality. And then for the upper bound, this is just a, we can use the e to the x squared Taylor expansion. And then notice that if we group these terms, these are all non-negative. And then so it follows that this, with these group terms, has to be greater than the 1, just the 1 plus x squared. And then so we drop these group terms and then just take the reciprocal of both sides with e to the negative x and the 1 plus x squared, and then we get this. So we've established that upper bound as well now. Okay, moving on. Oops, sorry. Okay, so now we're going to start transforming the inequality. So the first thing that we do is raise everything to the power of n, where n is a natural number. And then this is quite complicated. It's quite lengthy, the explanation of this. So I'm just going to be brief. So for this term, we use a trigonometric substitution over the interval 0 to 1. And 0 to 1, the reason for that is because it's positive and it simplifies it, but it's also 0 to 1 is our Laplace integral, which I'll come back to later. That will come clear, hopefully. So we do x equals sine cosine, and then we transform the derivative dx with a Pythagorean identity, and this is what we end up with. And then this middle term is just a normal u substitution. And then this term, similar to what we did for the lower bound, it's another trigonometric substitution. And then what we do is we create this variable wn, and wn, we set it equal to this. And now we rewrite this inequality with these 3 terms here. That becomes this. And it looks more complicated, but it actually helps us in what we want to do. And I'll get to why in just a moment. So just keep that in the back pocket for a second. So now we're going to come from the Euler's formula side of things and start to transform this. So this is Euler's identity or Euler's formula. So for this bracketed term, we do another trigonometric substitution where x to the power of x s is equal to cosine. And then just substituting, we end up with this. And then it's almost exactly the same for this right-handed bracketed term. We end up with this. And notice as well that this process is very similar to what we did for the asymptotic estimates inequality from earlier. We're transforming the expression, and as we integrate, we're using integrals of a power of cosine for our substitutions, which is essentially what we did for the previous inequality as well. So we end up with these 2 equivalent terms. And then we rewrite. This is the original form. We rewrite it. Now this is our transformed form. Okay, so now we're going to bring those 2 things together, those 2 transformed versions. We're going to bring them together now and show where this Euler's formula comes from. So this was the Wallace or asymptotic estimates inequality. And we had that, remember we created that variable here. And now we're going to do the exact same thing for this transformed Euler's identity. So we let Wn be equal to this, and we rewrite it. And we also just have this constraint now as well. And if we simplify it, we end up with this. So this is basically just, this is the Euler's form, is basically just a generalized version of this method of asymptotic estimates version here. So that's where Euler's formula comes from. And now we're going to show how we use it to solve. So we have Euler's identity here, and just note that that was the original version, not the transformed version. And we make this claim that as s approaches 0, 1 minus x squared approaches negative 2s ln x. And we prove this with just using L'Hopital's rule. We just differentiate. And then what we get is that when x is equal to 1, both sides of the expression is 0. So we can say that this claim is established. And now the r terms are just substituted with 0. And we're returning here to this Laplace form. I'll show that in a moment. But yeah, we sub in 0 for r, and then we substitute in that negative 2s ln x that we just proved the claim for. And now it's just a process of simplification. It's not too difficult. These terms are exactly the same, so we square them, then we pull out the 1 over 2s, and we get rid of the root because it's squared. and then we can just cancel because we have 1/2s on both sides, and we end up with this, and that's I squared equals that. So as you can see, I squared equals pi, and so obviously I equals root pi. And so that is why that original form from Laplace it is useful. It's not just a trivial sort of hidden Gaussian integral, but we did prove as well that it is pretty much identical to a Gaussian integral. So because we know I equals root pi, we can just do the same thing to
Thanks
prove
very
that
much for
e to
that,
the negative x
Brandon,
squared
Mabel,
is root
and
pi over
Eddie.
2.
That was awesome. Mabel, I just want to encourage you. I've worked with students from many different backgrounds. I've often done work with students over a number of years. And honestly, I've got nothing that I can say or see that
So
will
I think you're
encourage
muted,
you
Jason, if
any
you wanted to
differently.
ask any
You're
questions or
excellent.
anything.
You're very good. So thank you very much for your work, and just take some personal confidence. You're actually presenting a lot better than you are concerned about.